Let me see this, what this book says. 37. Yeah. Also, this book says that this partial derivative is equal to. Yeah, well, there is probably a typo. I will double check afterwards, and if there is something wrong in the solution, I will correct it and before uploading the file on the Canvas page. Yeah, that's what I do, especially with these books that they are literally done for just selling. Why there are 10 editions of these books and they're all the same, I don't know, but I don't want to talk about this otherwise. Okay, so somebody asked something. Okay, so well, the seminar is over for you. For those of you who want to go, you're free to go. I've just seen that Marcus sent out an email saying that the lecture of Friday is cancelled and also the seminar of Friday is cancelled. So this means that we will continue on Tuesday of the next week. So you have like almost a week to catch up, to redo the exercises, to try to do on your own the exercises from the sheet number 1. Important. Try to do exercises on your own because yeah, it's important. And that's all for today. To answer the question of somebody who asked if I could reiterate the subsequence rule. Jesper, are you still there, Jesper? Jesper, sorry. Okay. Right, so what's the role here of the sequences? So I'll open a box here and then I will cancel this. So you have seen in analysis 1 that let's suppose you have a function f of x. So the limit for x that goes to x0 of a function f of x is equal to L if and only if for all sequences xn with okay, for all xn sequences with xn going to x0, we have that the lim for n that goes to plus infinity of f of xn is equal to L, right? So a function has a limit if and only if this limit is, is the same along all the sequences that converges to x0, right? Now what I did is just, okay, you're free to prove this little proposition, but I think Jan Fredrik probably proved it. I hope he did. It's very interesting. So what I did is simply, I picked the two different sequences such that they both converges to 0, but the limit of the function computed in those two sequences, the two limits are different. One goes to 0 and one goes to 1. So I violated this proposition here. So that means that the limit does not exist because, yeah, that's the argument. If a limit exists, then it must be the same along all the sequences. If I find two different sequences such that the limit is different, then it doesn't exist. That's the same argument that we use to prove that a limit does not exist in several variables. We use curves, but you could as well use sequences. That's the same thing. I mean, they are all equivalent, these things. Is it clear? More? Less? Okay. Yeah, well, think about that. If you have still doubt, you can ask it again or just come here, swing by my office and yeah, how do I choose them? That's I choose them in a way that I produce different limits. I mean, I cherry picked them because I wanted, it's enough to find two, right? So I engineered them in a way that they have this property. You can see that an equal to 1 divided by the square root of 2 pi times n. If you plug this in into sine of 1 divided by an squared, you get sine of 2 pi n, and this is equal to 0 constantly for all n, because the pi, I mean, the sine is 2 periodic, and I'm just yes, and the same thing for the other one. It's 2 pi periodic, so yeah. Yes, so that's this is how I choose them. As I said, it's enough to have two, so you have freedom to select them as you want. So you want to display that something does not exist, you pick two different sequences such that they will lead you to different limits. So if I plug in the above lim, yes, you have to plug in this. Sorry, not this one. So you have to plug in this into sine of 1 divided by an squared, and this into sine of 1 divided by bn squared. Or yeah. So you can let me erase this box here. So you can simply define the function g of h, which is equal to sine of 1 divided by this, and then you compute g of an and the g of bn. And you see that g of an converges to 0, g of bn converges to 1 when n goes to plus infinity. And both an and bn goes to 0. That's what I did. Okay. All right. Very good. So if you don't have any more questions, thank you for today, and see you. There is another question, but this is yeah, all right. In example 3 and 4 for limits. Okay, well, you're free to go. I will answer to Emily privately. So let me see the examples that she's talking about. Example 3 and 4. Let's see. Yes, I'm uploading the slides this afternoon. Let's see this example 3. Bye-bye. Why did it change?